our second and the final panel discussion will focus on systems and training aids for transparent warfare. This session will be chaired by AVM Rajesh Sir, AVSM, VM, Distinguished Fellow, CAPS, New Delhi. Please welcome our esteemed panelist and the chairperson of the session on the stage, please. AVM Rajesh Issa, Shri Anurag Rana, co-founder, Threye Interactive, Lieutenant General V.K. Saxena, PVSM, AVSM, BSM, PhD retired, Shri Siddhesh Naik, co-founder, Ulook Technologies, Commodore Rajiv, Sreedharan, retired. I know we are less on the audience, but I think we can still have a big round of applause, ladies and gentlemen. Thank you. I shall now request AVM Rajesh to kindly conduct the proceedings.
Yeah.
So.
Good evening, everyone. And I've been told to really shorten the session if I want to be called again for the next conference or seminar that you have. So I'll reserve my comments a little bit, and we'll straightaway get on to the speakers. 10 minutes each. If you could just shorten this thing. And the only thing is, before they start, everyone's been invoking the Ukraine war and lessons learned, etc. I mean, it is the most transparent battlefield. Every eye, every sensor that you can speak of and you can dream of today in India are there, whether it's from the NATO side or the Russians. And the fact is, Kursk happened, Kursk, whichever way you pronounce it, and was it, if you take away the conspiracy theories that the Russians allowed it to trap them, the fact is, in a real battle, if you can hide your intent and surprise, there is a lot of scope for still conventional war. And even the war in Ukraine, the maximum attrition and the maximum, real battle casualties, etc., is happening because of artillery and other things like that. Still just like the conventional war. So basically it's a mix, and if uncrewed things have to make a difference, like somebody covered in the first session, just the Ukrainians, we are not talking about the Russians, are consuming more than 1,000 per month, and it is less. So that perspective must be kept, that we still have a long way. We have to scale uncrewed vehicles and produce in India. We are talking about producing, if you have to have, if they have to replace conventional artillery or air power or anything, they have to be in humongous quantities. Who's going to produce that? That's a big question. So without any further ado, may I request Anurag Rana of Threye Interactive, Threye Active, and be sure you talk of the glitch.
Hello. I'll absolutely run with it from here onwards. Some time ago it was said that pilots can introduce themselves. So I'm a pilot, and in this particular case I'm more over here as in my avatar of a game developer, a pilot and a programmer, and I'm gonna philosophize or hypothesize whether can we have a joint military metaverse or not. And before we do that, just a little bit about us. Threye Interactive is something which has been working with the Indian military for more than a decade now, for almost a dozen years. And the reality is that we have had a couple of successes, almost all of them exclusively with the Indian Air Force. But the fact is, these are the tip of the iceberg, those few successes that we can talk about, 10% successes. But the larger 90% failures that we have had over the last a dozen years or so have been all these multitude of NC demos, etc. And that's just about every startup story and all, etc. However, we persisted and we stuck around, and eventually some good fortune shined upon, for example, in this particular case, what looks like a beautiful effervescent watercolor painting of a military jet with light shining across in the form of IDEX, which happened just about 2 years ago. So finally, a lot of preparation came together when we were awarded under the DISC 5 category by the Honorable Defense Minister, both with the Indian Air Force, 2 programs on the Mirage 2000. And now I go back to the same image, which I just described as a beautiful watercolor painting. That's actually one of our art designers having fun, and he's just rendering a CGI image. So essentially, what are we talking about over here? We are talking about extremely high fidelity, not just visual fidelity, but dynamic fidelity simulations in this particular case, reacting to a problem statement which actually came from the Indian Air Force. The problem statement was, pilots obviously require very regular practice, and more importantly, they are now requiring practice of the type of group combat and large force engagements. However, they're not able to get realistic experience. Why? Because the scenarios that they need to do, either they're near the border or across the border, which is something that they cannot realistically actually carry out in practice, or it is just prohibitive either because of civilian traffic or just the logistics or the cost involved of taking so many airplanes. So pilots doing the training for a format of large force A versus B that requires 10, 12 airplanes on one side, 10, 12 airplanes on the other side in an actual combat-like situation, something which is not happening. And the idea was, do this, but go from what is onto the left, which is like a big dome full mission simulator, to onto the right, which is a large number of small PC-based simulators with an extremely high fidelity, perhaps 90% fidelity of the flight dynamics, but 100% fidelity of the man-machine interfaces. That includes all the man-machine interfaces, be it the stick, throttle, or your pages, etc. So we were equal to the challenge. And once again, I'll start with the graphic component, etc. However, what you're seeing on the images on the left over here is that it's actually superimposition of very optimized CAD modeling over an underlying point cloud model. So Air Force was gracious enough to let us access their cockpits, and we scanned these with either a laser with a 10 micron accuracy or with a lidar for larger, bigger areas that did not need that volumetric accuracy, and started modeling it. And to the right over here, you can see in terms of, slowly and slowly we're getting the material property. And over here, this is when it is fully modeled and then fully textured and fully lit. I would request your attention that you can see there is a boot pattern onto the left rudder pedal, because that is the kind of information we could capture and we could replicate. Now, this was a static model, but this is where the dynamic model is actually in flight. We have the terrain, we have the weather, we have day-night effect, we have internal controls with full lighting. Over here, you're seeing a lightning strike up ahead. And it is flying over a terrain, and this terrain, once again, has been fully built. Some of the areas which were very close to the ground have been made with an attempt that you could actually taxi, you could line up, you could take off, you could do your circuits, you can come back, and then you can do your dispersal, etc. There are about select few air bases which have been made in this detail, because the idea is that the missions are going to largely be taking off and they're going to be covering these particular scenarios. As I said, 100% fidelity of the man-machine interface. Most critical of that is obviously the stick, and starting with some very, very basic ideas in evolving from very simple 3D printing to getting the form and then getting the functionality right. This itself was a product in itself, and I think this consumed biggest amount of our time in terms of iterations, etc. So you wanted to get the right feel, and that essentially meant the gimbals over which it moves, the cam profiles, the springs to give you that tension, and all the complete functionality. The stick has close to about 9 buttons. The throttle has almost double of that, and many of these buttons have many dimensionalities. So, for example, there is a pointer which has front, back, up, down, and a press. So 5-dimensional fidelities and many such buttons, and everyone having a very different cap, so that pilot, when he's looking outside, he can feel it by his fingers, and then he has the right resistance. So while this itself would have been a product in itself, this was just one of the components. So I talked about beautiful art and graphics to have that immersion. I talked about all the man-machine interfaces. Now we'll come across to a very core important, which is dynamics. Now we are grateful to the Air Force for giving us this project. And it's just that they picked up one of the most difficult platforms. They picked up an unstable fly-by-wire airplane for which they actually do not have the OEM data. The data in terms of its NACA profile, what is the airfoil, at what angle of attack, what is the sort of coefficient of lift and drag, what are the aerodynamic forces that it produces. We did not have this data. What we did have were a lot of output charts which were given in terms of at this load, at this throttle setting, at this altitude, you're going to get this sort of a performance. You'll get such and such climb, you'll get such and such acceleration. But what we were expected is, we were expected to cover almost 85% of flight envelope for an unstable fly-by-wire enabled airplane, and give that realistic performance and feel to the pilot, for which we just did not have this data. So a parallel activity of this was, we also realized that we could not depend upon any third-party
flight data modeling, or we could not buy something and we just plug it. So we actually built all of these pillars from the ground up in our own simulator. So we built our own flight modeling characteristics, we built our own control system laws, and then after having so many knobs at our disposal is when we started tuning it, and so that the user could be happy. So we started with some pre-cut assumptions, models, either the models were of a certain fidelity or parameters were off, and we were getting quite a divergence in terms of the actual performance, but we slowly kept on fine-tuning, and this itself led to actual product, which is where a lot of these data modeling, which the fighter pilots are used to, for example, in this case, the doghouse plot, we actually converted that itself into a utility, and we told them, you tweak all these numbers and you get the performance curve you want, and just put that data file into this particular program and you're going to get the likely performance. Then again, this was a completely dynamic system, and then we had to go a typical characteristic of what you do to do your PID gains tuning, etc. You excite the system, you note the reaction, and then you put it into some sort of system ID, and from there you get your curve. So I'm doing this at a very, very super high level. This is obviously a tremendous amount of work and engineering which has gone across to realize this. I will very briefly touch, because man-machine interfaces where we were said no compromise whatsoever, 100% fidelity. So this is just an example of some of the MFD pages. Onto the left and on the right, you have some other systems. You have your fuel gauge, some engine parameters, and at the bottom, you have your common data unit where you typically put your nav data, etc. We went to the extent of that we had to make the custom font which Dasu uses in some of these heads-up display. We did not have that, so we once again reconstructed that. Now this program, this evolved with a very with a very iterative manner, and both at our premise as well as the Air Force's location. Indian Air Force, once again, they heavily tested it, and we gained from a lot of feedback. They brought their manuals, etc., flew the system, and they said at this particular point, if I press this button, this is supposed to happen, or if I turn this, I'm going to be pulling so many Gs, etc. And all of that data, we took it in our stride. We took the product to a certain maturity at our premise, and after that we took it to the Air Force's location. And not only the squadron which was championing this was the one which flying, and for us, which was a very welcome element, is because this was the Mirage, and there are 3 Mirage squadrons. When other squadron types came, they just took to it like a fish will take to the water. That itself was a testament that the man-machine interfaces, the stick, the throttle, etc., was of such high fidelity that they could almost feel it. Oh, this is like my airplane. I could just sit, I could take off, open throttle, I could carry out this mission profile, etc. They kept on giving a feedback. They kept on raising tickets and all. We took it in our stride, and this eventually matured in a product which was obviously fielded and sampled by the top echelons of the Indian Air Force, and eventually passed a successful trial, and which brought this IDEX program to its logical conclusion. This has resulted in a capability where we can now proudly claim that at least for this platform, we can sort of deliver any sort of a mission, any place in the world at any time. And in the process, we build those building blocks with which it is easy for us to replicate it to almost all fixed wings at the moment. And rotary aircraft is something that we are currently working upon. So this has been fielded by Air Force only at select events, where not only sister forces, they have come and sampled it, but also members of the friendly foreign forces, they have come, they have found it to be very potent, and there is an interest across over here. Very interestingly, we had to interoperate with a lot of other systems. So this interoperability was with a lot of GIS systems, with a lot of mission planning systems, with a lot of mission debriefing systems. So some of the protocols that we have used, they're very analogous to what NATO uses for their high-level architecture for their interoperability between different SIMs. This makes it very easy for us to scalable to what is called as live virtual constructive, in the sense of, again, some of the building blocks of the live virtual constructive is some of these high-level architecture modules, which are part of the interface of what we have built our distributed simulation systems on. Very high-level diagram in terms of what are some of the systems that we are using. The values of LVC are pretty much obvious in the sense of that you can, with this, interoperate between AI agents. With this, you can interoperate with your virtual simulators, and with this, you can also interoperate with your real systems. So a lot of systems that we are talking about that, hypothesis in the sense that if I'm going to be having a manned fighter, and if I'm going to be operating it with an unmanned fighter, what are the tactics that I can involve? What is the AI that I'm going to be putting onto that AI agent? All of those future technologies can be tested on this system now, and there's a complete roadmap in terms of how you test them in a simulation first, then how do you deploy them to scale models, and then how you can take it to the warfare. So everyone has talked about that. Obviously, warfighter is changing, and in this case, the warfare is changing much more than the warfighter. We are going to get there across over there, and there might be a little bit of sense in the sense of that the world has moved very fast. We might have got a little left behind. But I would say that the route from here to there goes through this matrix, or what I'm calling as the military metaverse. And with this, you can leapfrog, you can start testing those technologies, you can develop them, and you can start deploying them. And if the product is ready and the benefits are obvious, the only question is, we are ready with the matrix. The only question is whether the user is willing to take the red pill. That's it. That concludes my presentation. Thank you very much.
Nice one. May I request now Dr. General V.K. Saxena. I follow all his writings, so I am expecting something very good, but still, sir, 10 minutes.
All yours, sir.
Thank you, Chair, and good afternoon. Jai Hind to one and all. At the onset, my thanks to Siddhesh for providing me this opportunity to stand here and speak. My thanks also go to Shri Ashok Atluri, Chairman and Managing Director, Zen Technologies Limited, who provided me the honor and the privilege to stand here and speak for Zen Technologies on a topic which is slightly hatke, but really not hatke. It is intrinsically connected with transparent warfare. Zen Technologies, as most of you may be knowing, was incorporated in 1993, and we are in the business of making state-of-art combat training simulators for the training of defense and security forces worldwide. We are the leaders not only in combat training solutions, but also counter-drone solutions, also innovative force multipliers, and we are also into targeting, making surveillance system and state-of-art targeting capabilities. With 40+ systems designed and developed in-house, 1,000 systems deployed worldwide, and 161 patents in hand, we move on to do work which makes the nation strong. That is what about Zen Technologies. And now about my topic is green training, the new imperative. As I said, you might be finding this topic, how is it in transparent warfare? So I wish to start by finding relevance and a very strong connect between green training and transparent warfare. What is the relevance? What is the relevance here? We have been hearing very distinguished speakers and panelists here who have told us no end that for building the type of situational awareness, the type of absolute transparency in a battlefield, what we require, if I steal the words of Sujit, a cylindrical construct of surveillance system. Now, what is this cylindrical construct? This cylindrical construct has many layers, starting from the micro and the mini drones, then the small drones, then the ISTAR machines, that is intelligence, surveillance, target acquisition and reconnaissance machines in the HALA or Malay domain. Then a host of satellites, the HAP system, the LEOs, the satellites in the low Earth orbit, the medium Earth orbit, and the geosynchronous satellite. A huge lot of equipment is required to be deployed in a coordinated manner to construct the type of cylindrical construct of the surveillance system as Sujit talked about in his concept paper. Now, how this system is going to operate? This huge multitude of radars and systems, how they are going to operate? They will operate only as efficiently as the people who operate them. Man behind the machine is a motto which has never got diluted over the years. You will have radars, you will have surveillance systems, you will have drones going up, and you will have the control systems and the control stations controlling them. But what about the efficiency? We do not want the operators to simply collect the data. We want the operators who can interpret them, who can analyze it, and who are smart crews who can take action in time. We have been hearing the word collaboration. We are hearing the word collaboration to a large extent. I am talking of quality training of the persons who will operate this complete monolith of equipment which will happen. Now, to do this training, there are two modes available. Of course, the field mode training of all this, what does it require? What will it happen? You will have to switch on a large number of high volume radars. Radars which have worked with tremendous amount of electromagnetic energy. You will have to put the drones up. You will have to establish the ground control stations which control them. And you also will have to switch on many power supply systems, will have fuel guzzling generators. All of them will pollute the atmosphere a great deal. For this, at this point, the simulators, which Anurag just talked about a great deal, and he said anytime, anywhere for any mission, I will also say simulators are the key for effective and successful training. Why? Because simulators can not only reduce time and cost, they are also induce green training. What is green training? Green training is simulator-based training which reduces a huge amount of greenhouse gas emissions. How these greenhouse gas emissions take place? They take place when you ply the tanks. They take place when you move the vehicular fleet. They take place when you fire hundreds and thousands and millions of live ammunition. I stand here to say that simulators are not a total replacement for conventional training. Nothing can replace conventional training. Nothing can replace field mode training. If only a percentage of training is shifted to simulators, it can produce great amount of effects. That is why simulator training is called green training. Because not only it saves time and cost on a drastic scale, not only it can bring realism in the battlefield, not only it can yield objective results in your training performance, it also saves greenhouse gas emissions. And I am not saying this. The whole world is saying this. Why the whole world is saying this? Because we are on the cusp of evolving, ushering a green training revolution is in the making. What is this green training revolution? You must have heard of the Energy and the Resource Institute. This is a national level policy research institute which is working in the field of energy, environment, and sustainable development. Way back in early 2023, Zen Technologies tasked them to undertake a study of what is the environmental sustainability effect of simulators being developed by Zen Technologies Limited. What is the environmental sustainability? How will we sustain the environment? The results were astounding, to say the least. Let me take you through some key results and key findings. You'll find them very interesting. Okay, just to give you an idea, look at this slide and take an idea. One single round of INSA's 5.56 ammunition creates 216 grams of greenhouse gases, that is CO2 and other gases which do global warming and pollute the atmosphere. Imagine firing hundreds and thousands and millions of these rounds. Imagine the tanks ammunition, the BMP ammunition, the artillery ammunition, the air defense ammunition. I am not saying that there is a substitute to stop firing ammunition. No way. No way. The actual training, the actual validation of whatever you have learned comes in field mode training, comes in actual firing. But can you do actual firing really? In air defense, for the small arms, for the missile firing, the scale is 0.25 missile per firer per year. That means in 4 years, one missile firer will get one missile to fire. He needs to fire 100 missiles every day. How that is possible? That is possible through the use of combat training solutions. Now, let me go through this study. One vehicle training simulator, four-wheeled vehicle training simulator, over a 15-year period of time will save 103 tons of carbon dioxide and will amount to 56 lakhs in saving. What about a tank driving simulator? These are the astounding figures. 1990, and these are not some hypothetical figures. They have been done scientifically by Threye and experts on the field. That this is the type of saving which will be produced by one tank driving simulator. And what about the tank gunnery simulator? 3676 tons of carbon dioxide, 381 crores in 30-year period. So what is the return on investment? If you invest 15 crores into simulators life of 30 years, you will end up saving 380 crores of field mode training expenditure. Expenditure in terms of vehicle fleet, expenditure in terms of ammunition, expenditure in terms of movement, expenditure in terms of man costs which are involved. And this is 2,500% saving. something which should be astounding. Like I said, the results are astounding. Now, this is the type of revolution, this is the type of awareness which is coming into the armed forces. And also, armed forces and Threye is not alone. This whole thing is being taken up by Niti Aayog. The National Institute of Transforming India is also supporting the cause of green training. The government itself, on 23rd September 2021, have come out with a policy called Framework of Simulators in the Armed Forces. What do they say? They say that maximization of simulator culture in the forces, not only in the combat domain, but also in the administrative, maintenance and logistic domain must be ensured. This policy is under implementation. And Niti Aayog on 3rd December conducted a consultative workshop on green training initiatives. And they said that the green training initiatives of carrying out green training, carrying out smart waste management, carrying out adopting renewable energies should be the call of the day. So that is how I was talking about the green training revolution. And Zen technology is breaking new ground. What is that new ground? The new ground is we are trying to establish a national center for green training and environmental sustainability in the Threye premises in Gurgaon. This will be a center which will not only promote R&D activities on green training, it will be a center of excellence which will showcase various combat training solutions which produce green training effect, which will educate the audiences, national and international, which will train the forces, both security forces and paramilitary forces, on green training initiatives and technologies. Now, green training and transparent warfare, what is the connect? The green training connect is very simple. You people have talked, we all have listened to experts of transparent warfare. Simply it says you will require a huge amount of coordinated effect of sensors in, again I will use the word cylindrical construct of surveillance system. The training on the surveillance system and the efficiency of the trainers and the trainees will decide how good or bad the system will operate. My case here from this dais is that most of this training, as far as possible, should be green. Not only you will be saving a lot in time, in cost, in infrastructure, you will also be doing a national good for saving the environment. And that is why the topic is green training is the new imperative, green revolution is in the making, and I expect that the training which should follow should be green for all times to come. Thank you very much from my Cmde and from Zen Technologies.
Thank you, sir. Now I call on Siddhesh Naik, Ulook, right? Yes, Ulook Technologies. And this is very relevant. All these things about targeting and this thing on the battle space, today you're nowhere if space is not understood well. So here's an interesting company which is doing something good. So over to you.
Thank you, Chair. Good evening, everyone. Thanks, Amdis, for the opportunity to share my views here. Starting with the cylindrical construct, the last decade I've spent sort of loitering around near space, around the stratosphere, 20-kilometer range. With Ulook Ventures, I'm back to space. My first satellite was almost a decade ago. I'm an alumnus of University of Colorado at Boulder. Launched my first satellite through Laboratory of Atmospheric and Space Physics, one of the only non-NASA institutes so far to have an incredible record of sending payloads to all the planets in the solar system, including Pluto. Now back to the cylindrical construct. So with space, I'm going to talk about heterogeneous satellite swarms for near persistent ISR. But before I do that, a quick I'll sort of dial back to what Commodore Mahalankar addressed in his talk. The previous gen versus next gen. We're all familiar with monolithic structures or monolithic satellites, anywhere between 300 to 600 kgs, either in LEO or GEO, having lifetimes of a decade or so. A lot of us taking pride in designing those systems that last for a decade or so. Again, sitting ducks for sort of counter satellite, sort of anti-satellite weapons, counter mechanisms, and so on. That's sort of next gen, right? Costly, again, limited assets that you can deploy, very monolithic, very easy to shoot down, very easy to counter. Now, compared to that, let's look at some of the revolutions that have happened in the small satellite space. So if you look at the decade of 2000 to 2010, a new form factor of satellites emerged, known as nanosatellites. Now, nano really here refers to the size compared to what the existing class of satellites were. So these nanosatellites were the size of a shoebox, like literally something that could fit in my hand. CubeSats, as we all know them. The 2000 to 2010 decade, these were more of training aids to get graduate students skilled up and so on. The 2010 to 2020 is sort of what we saw as a technology demonstrator decade. So the industries, new space companies in North America and Europe sort of caught up and created these constellations which were 100, 150 in numbers, right? And at some point, a company had 150 plus nanosatellites that were imaging every point on Earth with a certain resolution. But that sort of, we saw the last decade as the technology demonstrator phase of these satellites. What this decade is going to really, what we're going to see is operationalizing of this space, right? You're going to have not tens or hundreds, but multiples of these satellites. And again, those will have its own technological challenges. They'll also have their operational challenges. Just because the number of satellites are increasing doesn't mean your ground stations are gonna grow up, or the number of operators are gonna grow up. They're not going to scale the same way. So a lot of autonomy, onboard decision making, their ability to share information with each other and collaboratively work together is going to emerge. And that's where the concept of satellite swarming starts coming in. We're all familiar with the concept of satellite constellations. You have multiple of these satellites sort of distributed around the Earth that sort of give you, say, a 24/7 or a near Earth coverage. What we're looking at here is a cluster of satellites, which sort of in the old way of doing things resemble a single satellite. So you have a cluster of satellites. When I say heterogeneous, we talk about different payloads. One, they're talking to each other. So they have inter-satellite links. They're sharing information in real time. They also have a lot of onboard decision-making capability. So they have a sort of hive mind capability. Now, the first satellite swarm mission, sort of a technology demonstrator, was something as recent as August last year. This was a NASA Starling mission that demonstrated a swarm of 4 CubeSats. Our Defense Space Agency is not very far off. They have launched a mission Dev Space Challenge, which again, which has a program on autonomous CubeSat swarms. So in that sense, this is really the next gen of satellite or swarming technology. Now, in terms of applications, before we get into the sort of con-ops of this, let's look at what typical sensors give you, right? So that essentially 2 kinds of sensors, active and passive. If you just go with active or remote sensing imaging sensors, let's starting with EO sensors, these typically have sort of swaths of anywhere around 10 to 15 kilometers. We start going a little coarser in images, those swaths get to about 100 kilometers. We go to wide area SAR sensing, they go about 150, 200 kilometers, and so on. Off late, what we've seen is RF satellite swarms, which have swaths of about 1,000 by 1,000 kilometers. So how a heterogeneous satellite swarm really works is it marries these 3 different satellites having these 3 different sensors as a sort of a one cohesive unit. So imagine an RF satellite that can image, or not image, that can, say, monitor an area of 1,000 by 1,000 kilometers instantaneously. It's looking for, say, rogue elements. It's looking for, say, dark ships. It's looking for any sort of emitters. They give you the tip, they sort of tip and cue the next layer for sort of further investigation. So the RF sensors with sort of their broad sensors and broad coverage then can tip and cue the next line of sensors. It could be SAR, it could be EO. So it's their ability to task each other in real time, in space, autonomously, is where a lot of swarming capability exists. Now, we've seen these kind of operations already demonstrated offline. We've seen a company called Hawkeye 360 pick up certain signals of interest in our northern regions, then tip and queue the imaging satellites, and then gather more information and so on, right? Now this has taken about, this whole process typically takes 10 to 12 days for the entire cycle to correct out. You collect the RF data, you analyze it on ground, you tip and queue the next layer, that data gets collected, analyzed, and then any actionable insights, if so, were to emerge, really emerge. What we're talking about is a swarming cluster that can autonomously task each other. So the base of this cluster is a RF sensing layer, which picks up the emitters of interest, then tips and queues the next layer. It could be an imaging layer, it could be a SAR layer, depending on, again, the autonomous nature of it gives it the ability to task the right sensor, the right platform having the right sensor. In a day and night operation scenario, you look at a SAR image. For further, again, very finer extraction of features and details, you look at imagery. So again, this is something, so while we are talking about the 55 satellite SBS3 effort and so on, again, everything in the right direction, that's, if you see on a global scale or in terms of what's happening, it's still sort of previous generation, right? When we talk of next gen in this domain, it's going to be swarms, it's going to be satellites that are going to be agile, that are going to be reactive to situations, that are going to be autonomously think and give you that real-time sort of feeds and insights. Just to put a few things into comparison, when we generally think of satellites, we think of humongous capital expenditure, and that's rightly so. When we talk about a 300, 400, 500,000 kilogram plus satellites with certain desired lifetimes, those are the numbers we come up with, right? But with the next generation of satellites, when you look at replenishment times of 3 years, we look at smaller platforms, but capable platforms, say around 30 kilograms, 50 kilograms, an entire constellation that gives you, say, a near revisit capability in our IOR region of about an hour or less, is a fraction of a cost when you start talking about platforms like a P8 or RQ9 or on a comparative scale. Again, that's the power of what smaller platforms, more distributed platforms can give you. The more distributed they are, more resilient they are to any counter attacks. This is about space, from space on Earth, right, from an ISR perspective. The other areas where satellite swarms, again, can start making a huge difference is in the ability to carry out policing actions. When we're talking about certain assets, it could be GEO, could be LEO, which are going to be critical for our operations. We're talking about move from a network-centric warfare to a data-centric warfare and so on. There are certain assets which are going to be critical, and we will need to develop ability to defend these, if not carry out an offensive action. A satellite swarm simply with its ability to carry out coordinated, close sort of RPO operations can act as shields. And sort of I'm giving out very plain, high-level thought process in terms of how these swarm of small nanosatellites could really be deployed for a lot of policing actions. The ability to sort of watch out, investigate assets, again, non-invasively. The sort of imaginations it's sort of left to our imagination in terms of what the applications could be. Me and my co-founder, we bring about a heritage of 15 LEO satellites, of course, from the North American continent. But we're based out of Bangalore. We're trying to explore these concepts. Some of it already has resonance with the agencies. And again, this is an exciting time, right? Sort of just adding it there, leaving it there on the last minute under the time constraint. We're talking about transparent warfare. We're all talking about our current sovereign borders. We also have to start looking at aspects of cislunar, or sort of the emerging areas and domains where we'll have to assert our sort of our sovereignty, or ensure that our interests are protected. And to that effect, if we see globally, missions have already started to sort of track these areas in terms of what the adversarial nations are doing, what assets are flying, what the typical trajectories are, and so on. So again, to maintain transparency, at least to us in terms of what's happening in a lot of these areas, which are going to be contested in future, we also have to start thinking about technologies that can support this. Swarming at whole or at large can achieve a lot of things, and swarming again is sort of a very broad concept. But again, things to ponder over for this forum in terms of how we want to move forward. Again, very different than the classical ISR role that it plays within sort of our current doctrine and so on, but food for thought. Thank you.
Thank you, Siddhesh. Now we have Commodore Rajiv Sreedharan, retired GRSE, and he's going to talk about stealthy ships or something to that effect. Let's hear him out.
My co-panelists and ladies and gentlemen, good afternoon, and I thank Samdes for giving me this opportunity to speak about this topic, which is called low emissions, less observable, optionally manned ships. So me from GRSE, we are shipbuilders. We are a lot of naval officers also there. Our ex-chairman is sitting here. So we are, our ACWP&A is sitting here, and a few naval officers, senior naval officers here, who can understand the pain of designing vessels and now to make it less, with low emission, less observable, and optionally manned is a great challenge. We're doing it in bits and pieces, and where we are today and where we need to go. I'll quickly, I will cut off a lot of details and quickly wind up, sir, because I understand the difficulty. Now, as far as the topic is concerned, low emission plus less observable plus optionally manned. Now, the whole thing revolves around ship survivability. What is ship survivability? It is the ability of a ship and its systems to remain operational and continue its mission in a hostile environment. So, low emission plus less observable means stealth, and optionally manned is autonomy. Now, stealth is directly related to survivability of a vessel. So, this is where the designer comes in. Now, survivability has two aspects. One is the operational aspects, one is the design aspects. The operational aspects and design aspects are embedded into all the factors that cover survivability. The first four green boxes are aspects which are fundamentally aspects that avoid detection or delay the detection of a vessel, and in case it is detected, to kill the weapon which is kind of trying to home onto the vessel. Now, that is essentially the susceptibility of the vessel, and the other aspect is that of the vulnerability. That means in case you get hit, how can you effectively sustain your operations to the extent that is feasible? And the third part is to recover from a damage. Now, all these aspects are what goes into the eventual survivability of the vessel. Now, the ship lives in a very dense signature shell, and that is getting worse as we speak, because initially when we were young naval architects, we used to only talk about magnetic, wake, and a few other things. Now we can detect the vessel from, as he just mentioned, from outer space. So, so this entire signature shell is getting more dense, and as ship designers and shipbuilders, we try to address these issues and make it more stealthier. The detection technology is getting more and more, sophisticated, and is always leading the pack. So we are always playing catch up. So in a naval environment, in a ship, you have all the three dimensions: the subsurface, the surface, and the air threats. Now, the whole issue of the whole challenge is to get detected later, and if at all you're detected, to kill the weapon. So this is what I'm not going into details because we don't have the time. Now, some of the quick issues which I want to just highlight, will not go into details again, is only the different types of signatures. The IR is something that has been there for a long period of time. And now if you see, if you don't have any IR suppression methods, you get the missile locks on and you have just 8 seconds to react to fire your flares. And in case you have the active cooling system, which is the plume cooling of your exhaust with IRSS devices, and also active hull cooling, which is like cooling the entire shell, then you have about 70 seconds to react. So this is the kind of timelines that we are talking about. So all these needs to get, you need to cater into your designs. The other part is the electric signal. All of us are familiar that when the shaft is rotating and when we have the shaft is a naked piece of metal, and we have cathodic protection. Because of this interaction, you have very low frequency emissions which are carried across huge distances and get detected. So we have these active shaft grounding systems, but now there is another challenge. When the active shaft grounding systems is working, then again there are ripple effects and all those things. I will not get into details, but that it's all evolving, as because people pick up these signals and then kind of target you. All of us are familiar of RCS because it's a very familiar topic for the aviators as well. We deal with hull shapes, the radar absorbent material which Professor Ray just spoke about some time back. We have interesting, that is integrated mass. Now all of us must have heard of this unicorn that we are getting from Japan, which is an integrated mass. The typical mass that you see is on the left side, and what would eventually come is this. So it is very stealthy, and the integrated mass is something that we are also working on as a country, and I think shortly we should have it in our ships. The aspects of being picked up from all this we can do, and we have been doing all this for quite some time now, and we are only improving as our new designs come up. But now you do everything, and the Chinese, so-called stealthy vessels are picked up by satellites and they have the entire details at where it is and where it's moving and all those things. So this is what we land up even after we make all these efforts. But that's how technology is. So magnetic signatures, we are doing degaussing system, deperming. Again, because we are doing degaussing, we are injecting current, and again that has ripples. Now how to suppress those ripples is another challenge, and it's an endless cycle. So we'll not get into details again. I'll go fast on all these things. Another major issue for us as shipbuilders, ship designers, and the naval operators is underwater noise generation. That is structure-borne noise, airborne noise. Now we have a lot of things that we do. I will not get into details again. We have a lot of technologies, including injecting air bubbles into the propellers to delay the cavitation or suppress cavitation noise. We have maskers which are injecting bubbles on the surface of the hull, and which creates an impedance difference between the hull and the water, so you don't transmit noise. Then there are standard noise control measures. I'll just skim over that, and then we go to now. Important aspect is talking about what is this relationship about stealth and autonomous vessels. Essentially, autonomous vessels are stealthy by definition. I would like to call it by definition, but of course you can build anything without taking care of things and it makes it non-stealthy. By definition, they are stealthy because they have a low observable design. They don't need a superstructure. They don't need bridge. They don't need, of course, we have come to the optionally manned aspects. But if you talk of a simple, straightforward, autonomous vessel, we don't have superstructure, which stands out of the water, no requirement for accommodation because you're not having people, and that is the most complex thing to handle on a ship. So many people, their domestic requirements, and things like that. The small size of these vessels also lend it favorable for us to design it with composites, which reduce magnetic signature. Of course, the challenge of composite not being green, etc., is something that we later handle. Then it also has low wake because small vessels, we can use catamaran designs, trimarans, we can do a whole lot of things to design the hull so that we have low wake. We can also have minimal underwater radiation noise because we can go in for electric propulsion or other the power itself required is significantly low, so you don't generate so much of noise. We also don't need air conditioning systems, we don't need other auxiliary systems, so they're inherently quiet platforms. And as a result, you'll have low IR signature as well. So USVs rely on less recoverability. We don't have people on board, so if you get damaged, you're just damaged. You can just sink. There are no people to intervene. And they don't have they have low self-defense capabilities. They cannot intelligently, neutralize a threat. So the entire aspect of this, of USVs or AUVs are low susceptibility. That means you don't get it detected. So then that increases the let us say, the potency of these platforms. So what are the key drivers? They can be deployed where crews are not put in harm's way, as we may call it. They can fulfill roles that fit into the 6 Ds, that is distance, detection, defense, distribution, delivery, and decision advantage. They can process data very quickly, analyze, and deliver decisions. Of course, supervised. It has asymmetric advantages in the distributed maritime operation scenario, and it can be enormously cheaper as they can be produced, and they can therefore be produced in large numbers to generate mass. So this is the advantage, again, going into the scenario that was just spoken about a great deal today, is about the Ukrainian example. So you can just produce them in large numbers. And because they are cheap, attrition can be easily offset. Now, these are, I'll just rattle them out so that, I'm not getting into details. What are hybrid threats? Yes. So what are the hybrid threats? All of us know. Now, where we are looking at contributing as a shipbuilder is in the anti-submarine warfare, naval mine countermeasures. These are things that are actually required for the Navy. And of course, other things are all kind of fallout of the design of these vessels. So specifically the issue of optionally manned, we never thought about it as shipbuilders till now, until the challenge was posed by Commodore Samadhar today, or a couple of days back. So this optionally manned is essentially where because we have the large number of, the Navy is looking to put large number of vessels at sea, and they can, carry missiles and, weapons of mass destruction over large spans, distributed areas, without making it complex. They don't need to have self-defense. They just need to be dummies. They just need to fire when you give a command from somewhere remote. So that is something which is a concept for the large USVs which the Navy, which the US and the Australians are looking at now. But it is also that, although it is cheap, if you want to look at large numbers, some of the smaller navies cannot afford it. So you need to use these vessels to do multiple roles, which makes it convenient if you have an option to make it optionally manned. So this is the reason why I'm talking optionally manned, and I'll just give me 30 seconds more, sir. We at GRSE, being shipbuilders, we are already into building autonomous vessels, both surface and subsurface. And this is a Jaldoot, which is a small USV. It's a mothership. It's a vessel which can communicate between the USVs and when submerged and transmit data to a mothership. It is delivered to NSTL recently. Swadhin is another USV that we have. It can do essentially bathymetry. It's got multi-beam echo sounders and can do autonomous navigation, can do survey of large areas. We are also working on the ASV MCM project for the Indian Navy Make 2, HE AUV Make 2 project. Nirakshi is two versions that we have. These are AUVs which can go up to 300 meters. And you can see that it can do seabed scanning, underwater communication, obstacle avoidance. It can do a lot of missions. And this is the latest that we have, and we have tested that and doing pretty good. 300 meters depth. It's got a side scan sonar, acoustic modem, Doppler velocity log, HRS, and depth sensors, etc. So it's quite densely packed. It can do a whole lot of missions depending on the requirement of the user. So I think with that, I'll just conclude. basically USVs and UUVs or AUVs as we call them will provide Navy's formidable advantage at sea because of, as I said, numbers, cheapness, and it's not easily detectable. However, if the challenge of UUVs and AUVs not being detected is also something that we need to counter with other smaller AUVs or things like, because you cannot use huge weapon systems to destroy them. So it's again a bit of a problem, but that is how we go. And optional manning will provide flexibility and affordability for fleets, and vessels with weapons and launch capabilities and swarms are imminent in the future. Now there are two challenges here. The shipbuilders need to, need to grow in terms of technological competence and capability to build this, and also a big issue of consolidation. Now, if there are 10 people in this country working on AUVs, 10 people working on, we need to consolidate the technology and build as a nation. So that's something that we need to think about. Thank you, sir.
Thank you, Rajiv. We've heard some excellent presentations despite the few glitches around. Anurag, I think it's a lovely story of how collaboration with the user and creative designer at work, it can provide miracles. And of course, a very new topic by General Saxena of green training. Though I'm glad he put the caveat that it can only supplement, a percentage. There is nothing that can replace real training, and actually there is nothing that can replace real battle experience. I mean, those who experience battles will vouch for this. And of course, our own Elon Musk here, who gave a very disruptive, I hadn't heard of this, swarming and intelligent satellites doing what we are still talking about on the ground. And that's a great thing. And of course, your stealthy ships. I'm glad you're the only person today who's spoken about opacity rather than transparency. This is how to beat the transparency, which is equally important. It's an industry in itself. And I'll close by just one example. Finally, somebody said in the morning, it is the men who apply the technology, even if it is a lower end or higher end. You can see it in Ukraine, you can see it. We saw it when I saw Sam Manekshaw's portrait there. 1971 war, we just crossed a Vijay Divas. Those who remember General Sagat Singh, I mean, he was a man who was not supposed to do anything, was given a few helicopters, and Dhaka fell because of him. I'm convinced, I'm ready to debate this with anybody. Done enough historical analysis of this. And so it is, we got to train our people on uncertainties or two. How to be very, very comfortable with uncertainty and innovate tactically. That's what's going to win wars. Technology is very, very important, there's no doubt. But how that is going to be applied, we needn't be the best of technology, even with somewhere halfway there. If we have the best of generals and air marshals and admirals, I think we are good. Thank you very much. Yeah, a hand for the entire panel. Wonderful. Thank you.
Thank you, dear panel members, for that very insightful session. May I request Ms. Shobna Joshi to kindly felicitate our panel members. To AVM Rajesh Isar. To Shri Anurag Rana. To Lieutenant General V.K. Saxena. To Shri Siddhesh Naik. to Commodore Rajiv Sreedharan. May I request the panel members for a group photograph, please? Thank you very much, dear panel members, and thank you, Mr. Joshi. With that, we conclude the final panel discussion of the event today. We thank all the speakers and participants for the insightful contribution here.